Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll explore how Amazon Redshift Spectrum empowers you to seamlessly analyze vast amounts of data stored in Amazon S3 without the need to load it into your Redshift data warehouse. You'll discover how Spectrum extends the capabilities of your Redshift cluster, allowing you to run fast, complex SQL queries directly on structured and semi-structured data in your S3 data lake. We'll cover the core architecture, key features, and practical use cases, showing how Spectrum can help you unlock insights from petabyte to exabyte scale datasets with high performance and cost efficiency. Let's get started. Amazon Redshift Spectrum is an advanced feature that extends the power of your Redshift data warehouse, enabling you to run fast, complex SQL queries directly against massive datasets stored in Amazon S3 without the need to load or transform that data first. Spectrum achieves this by separating compute from storage. When you submit a query, Spectrum automatically provisions a fleet of AWS managed servers separate from your Redshift cluster to scan, filter, and process the data in parallel. This massively parallel processing architecture allows you to efficiently analyze data at petabyte scale, dynamically scaling resources to match your workload and ensuring your Redshift cluster performance isn't impacted by external queries. One of the core strengths of Spectrum is its seamless integration with external data catalogs like AWS Glue or the Hive Metastore. This integration makes it easy to define external tables that point to your S3 data, so you can immediately query new or updated files without any ETL or data loading overhead. Spectrum supports a wide variety of file formats, including Parquet, ORC, JSON, CSV, and Avro, as well as complex nested data types, giving you the flexibility to store and analyze your data in the format that best suits your needs. Spectrum is also highly cost-effective. You only pay for the amount of S3 data scanned per query, with no upfront infrastructure or ongoing maintenance costs. Performance is further optimized through techniques like predicate pushdown and partition pruning, which minimize the amount of data that needs to be scanned and transferred. Security is robust, with full support for IAM roles, AWS KMS encryption, and fine-grained access controls to ensure your data is protected. With Redshift Spectrum, you can seamlessly join data from your Redshift warehouse with data in your S3 data lake, enabling truly hybrid analytics and unlocking insights across all your AWS data assets, no matter where they live or how large they grow. Amazon Redshift Spectrum architecture enables users to run SQL queries directly against exabyte-scale data in Amazon S3, seamlessly integrating with Redshift's managed data warehouse. Here's how the architecture works, layer by layer. At the top, the client layer represents various client applications, such as BI tools, SQL editors, or custom analytics dashboards that connect to Redshift using JDBC or ODBC connections. These clients interact with the Redshift cluster to submit queries and retrieve results. The Redshift cluster layer is the core of the managed data warehouse. It consists of a leader node and multiple compute nodes. The leader node coordinates query execution, distributing work across the compute nodes. This layer handles queries on data stored locally within Redshift tables, providing high performance and scalability through Redshift's cluster scaling. Below the Redshift cluster, the Redshift Spectrum layer enables independent, elastic scaling for querying data directly in Amazon S3. When a query references external tables, data stored in S3, Redshift Spectrum spins up multiple worker nodes to process the data in parallel. This layer operates independently from the Redshift cluster, allowing for flexible and scalable compute resources specifically for external data processing. At the storage layer, Amazon S3 provides exabyte-scale durable object storage for raw and processed data. Redshift Spectrum accesses data directly from S3 buckets, allowing users to analyze vast amounts of data without loading it into Redshift. Finally, the data catalog, such as AWS Glue or a Hive Metastore, acts as the metadata repository. It stores schema definitions and table metadata for the external data in S3, enabling Redshift Spectrum to interpret and query the data efficiently. Designing an efficient data lake for Redshift Spectrum involves several advanced strategies to ensure high performance, scalability, and cost effectiveness. One of the most critical aspects is implementing optimal partitioning strategies. By partitioning your data along frequently filtered columns, such as date, region, or business unit, you enable Spectrum to scan only the relevant slices of data, dramatically reducing both query time and cost. Taking this a step further, multi-level partition schemes, like organizing data by year, month, and day, or combining time-based and business attributes, allow for even finer granularity. This hierarchical approach enables Spectrum to prune partitions at multiple levels, ensuring that only the necessary data is accessed for each query. Another key practice is file compaction. Over time, data lakes can accumulate many small files, which can negatively impact Spectrum's parallel processing capabilities and increase query overhead. Regularly compacting these small files into larger ones, ideally between 128 megabytes and 1 gigabyte, helps maximize throughput and fully leverage Spectrum's parallel architecture. Choosing the right compression format is also essential. Compression algorithms like Snappy for Parquet files not only reduce storage costs, but also support fast parallel reads, which is crucial for Spectrum's performance. Always balance compression efficiency with the need for quick data access. Data layout optimization further enhances performance. Storing data in columnar formats such as Parquet or ORC allows Spectrum to take advantage of predicate pushdown and efficient columnar reads. Additionally, organizing your S3 folders and files to reflect common query patterns ensures that partition pruning is as effective as possible. Don't forget to set table statistics for your external tables by manually specifying row counts. This helps the Redshift optimizer generate better query plans, as analyze is not available for external tables. Finally, continuously monitor query performance and be ready to adjust your partitioning, file sizes, and compression choices as your data and workloads evolve. These advanced design techniques will ensure your data lake remains high-performing, cost-effective, and fully optimized for analytics with Redshift Spectrum. When optimizing your data lake for Redshift Spectrum, choosing the right file format is essential for both performance and cost efficiency. Let's start with a quick comparison. Parquet and ORC are both columnar formats, which means they store data by columns rather than by rows. This structure allows Spectrum to read only the columns needed for a query, resulting in significantly faster performance and lower costs, especially for analytical workloads. ORC offers slightly better compression and built-in indexing, making it a strong choice in Hive-centric environments or for queries with heavy filtering and aggregation. Ever, on the other hand, is a row-based format. It's excellent for streaming ingestion and scenarios where schema evolution is frequent, but it's less efficient for analytics because Spectrum must read entire rows even if only a few columns are queried. Diving deeper, the internal structure of these columnar formats also matters. Parquet organizes data into row groups and pages, enabling efficient predicate pushdown and column skipping. ORC uses stripes and built-in indexes, including Bloom filters, to further accelerate selective queries. Both formats support rich metadata, which Spectrum leverages to optimize scans and reduce I/O. To get the best performance from Parquet, use multiple, evenly sized files, ideally between 128 megabytes and 1 gigabyte, to maximize parallel processing. Apply snappy compression for a good balance of storage savings and read speed, and design your schema and partitioning to match common query patterns. For complex nested data, both Parquet and ORC natively support arrays, maps, and structs, making them ideal for semi-structured data analytics. If you're ingesting raw data in Avro, consider converting it to Parquet or ORC using ETL or Spark jobs for downstream analytics. Finally, Parquet is generally the best choice for Spectrum queries, with ORC as a strong alternative. Use Avro for ingestion and schema evolution, but convert to columnar formats for high-performance analytics. Optimizing queries in Redshift Spectrum requires a deep understanding of how Spectrum interacts with both S3 and your Redshift cluster. One of the most effective techniques is predicate pushdown. When you use filtering conditions in your SQL queries, such as where clauses, Spectrum attempts to apply these filters directly at the S3 layer. This means only the relevant subset of data is read and transferred, significantly improving performance and reducing costs. However, not all operations are supported for pushdown. While most basic comparisons and simple functions like count and sum are pushed down, more complex operations such as distinct or order by may not be, so it's important to check your query plans and adjust accordingly. Join optimization is another crucial area. When joining Spectrum external tables with local Redshift tables, always try to filter and aggregate the external S3 data before the join. This reduces the amount of data that needs to be moved and processed by your Redshift cluster. Using compatible distribution and sort keys can also help enable more efficient merge joins, minimizing data shuffling and improving overall performance. Aggregation pushdown is a powerful strategy as well. By using aggregate functions like count, sum, or average in your queries, you can offload heavy computations to the Spectrum layer, freeing up your Redshift cluster's resources and speeding up query execution. When dealing with complex filtering conditions, break them down into simpler predicates that Spectrum can push down. Always leverage partition columns in your where clauses to maximize partition pruning. Avoid using functions or expressions that prevent pushdown, and use explain plans to confirm your optimizations are effective. Since Analyze isn't available for external tables, it's important to manually set row counts and other statistics for your external tables. Accurate statistics help the optimizer generate efficient query plans, especially for joins. Regularly update statistics on your local tables as well to maintain optimal performance. By applying these advanced techniques, you can ensure your Spectrum queries are both fast and cost-effective, even as your datasets grow in size and complexity. Redshift Spectrum isn't just about running simple queries on massive S3 datasets. It also empowers you to perform truly complex analytics at scale. One powerful capability is the use of window functions directly on external data. With functions like row number, rank, and list aggregate, you can generate rankings, running totals, and cohort analyses across billions of records stored in S3, all without moving data into your Redshift cluster. Spectrum also supports recursive queries and complex joins, enabling you to analyze hierarchical data structures, build recommendation systems, or merge information from multiple disparate sources. By joining external S3 tables with local Redshift tables, you can build rich, multi-layered analytics pipelines that leverage the strengths of both storage locations. Geospatial analytics is another area where Spectrum shines. With support for Redshift's geography data type and spatial functions such as stcontains and stdistance, you can run advanced location-based queries on large external datasets. For even better performance, consider partitioning your spatial data in S3 by geographic boundaries, so Spectrum can quickly zero in on relevant regions. Temporal data analysis is made easy with Spectrum's ability to efficiently query time series and event data. By partitioning your S3 data by date and leveraging Redshift's time-based functions, you can analyze IoT sensor streams, financial transactions, or user behavior patterns with minimal overhead and maximum scalability. Finally, Spectrum is a powerful tool for machine learning feature preparation. You can join and transform large feature sets directly in S3, combining them with local Redshift tables as needed. This streamlines the process of feature engineering for machine learning workflows and integrates seamlessly with Redshift ML or SageMaker Feature Store for scalable model training. Redshift's federated query architecture is designed to break down data silos and enable seamless analytics across your entire data landscape. With Spectrum, you can already query data in S3 alongside your Redshift tables, but the power of federation goes even further. You can now integrate multiple data sources, including Amazon RDS, Aurora PostgreSQL, and Aurora MySQL, directly into your Redshift queries. This means you can join live transactional data from operational databases with historical or analytical data in S3, all in a single SQL statement, without the need for complex ETL pipelines. Consistent metadata management is critical in a federated environment. By leveraging the AWS Glue Data Catalog or Redshift's external schemas, you can maintain a unified view of your metadata across all data sources. This ensures that your queries are reliable, repeatable, and easy to manage as your architecture evolves. Federated queries also allow you to span multiple Redshift clusters, making it possible to unify analytics and reporting across different business units or geographic regions. For organizations operating in multiple AWS regions, cross-region query strategies such as VPC peering and enhanced VPC routing enable secure, low-latency access to remote data sources. This flexibility is essential for global enterprises that need to analyze distributed datasets in real time. Redshift's federated query engine is optimized for performance. It pushes down predicates and filters to remote databases whenever possible, minimizing data movement and leveraging parallel processing to accelerate query execution. You can also apply lightweight transformations and filters on live data, reducing the need for pre-staging or batch ETL jobs. By adopting a federated query architecture, you can deliver real-time, unified analytics across operational databases, data warehouses, and data lakes, empowering your teams to make faster, data-driven decisions. Integrating an advanced data catalog is essential for managing metadata, ensuring governance, and streamlining analytics across your AWS environment. At the heart of this integration is the AWS Glue Data Catalog, which serves as a centralized repository for all your schema and table definitions, making it the single source of truth for your organization's data assets. By leveraging glue crawlers, you can automate the discovery of new data in your data lake. These crawlers scan your S3 buckets, infer schemas, and automatically update the catalog, ensuring that Spectrum and other analytics services always have access to the latest metadata without manual intervention. Schema versioning and evolution are also key benefits of advanced catalog integration. The Glue Data Catalog tracks changes to your schemas over time, allowing you to manage multiple versions and maintain compatibility as your data evolves. This is especially important in dynamic environments where data structures frequently change. Fine-grained access control is another critical feature. With AWS Lake Formation and IAM, you can enforce security policies at the database, table, column, or even row level, ensuring that users only access the data they're authorized to see. The Glue Data Catalog also supports cross-service integration, sharing metadata seamlessly with services like Athena, EMR, and Redshift Spectrum. This unified approach enables consistent data governance and discoverability across your entire analytics stack. Efficient partition management is another advantage. By automating partition registration and updates, you ensure that queries benefit from optimal partition pruning, leading to faster query performance and lower costs. Finally, catalog metadata can be used for data lineage tracking and auditing, providing visibility into how data flows through your environment and who accesses it. Regularly cleaning up unused tables and partitions helps maintain catalog performance, ensuring fast metadata lookups for all users. Redshift Spectrum offers remarkable flexibility for building modern data pipelines, supporting both ETL and ELT patterns to fit your organization's needs. In a traditional ETL approach, you might use AWS Glue or EMR to transform your data before loading it into Redshift. This is ideal when you need to leverage specialized transformation tools or want to pre-process data outside your data warehouse. On the other hand, with an ELT approach, you can load raw data directly into S3 or Redshift and then use SQL and Spectrum's external tables to transform and aggregate data in place. This leverages Redshift's powerful, scalable compute and is highly efficient for large-scale, SQL-driven workloads. Spectrum enables you to run SQL queries and transformations directly on S3 data, reducing unnecessary data movement and supporting scalable batch processing. For large periodic workloads, you can even spin up temporary Redshift clusters, process or aggregate S3 data using Spectrum, unload the results back to S3, and then terminate the cluster to optimize costs. A key best practice is to use open, analytics-optimized file formats like Parquet, ORC, or Avro, which are fully compatible with Spectrum and downstream analytics tools. When it comes to sharing or exporting curated data, the unload command lets you export query results from Redshift to S3 in parallel, partitioned and in columnar formats. This makes it easy to share data with services like Athena, Glue, EMR, or SageMaker. Optimize your unload operations by partitioning output, balancing file sizes, and securing data with encryption and IAM policies. A powerful pattern in these workflows is using CTAS or create table as select. CTAS lets you pre-aggregate, filter, or reshape large external datasets, storing the results as new Redshift tables or optimized files in S3. For best performance, select distribution and sort keys that match your join and filter patterns, and store output in compressed, columnar formats like Parquet. Partition your CTAS output by frequently queried columns, such as date or region, to enable efficient partition pruning and speed up future queries. One of the most transformative capabilities of Redshift Spectrum is its ability to decouple compute and storage at scale. This is especially valuable for multi-cluster patterns, such as isolating dev, test, and production environments, supporting both analytics and machine learning workloads, or providing departmental autonomy without duplicating data. With Spectrum, your data lake becomes a central source of truth. Multiple Redshift clusters can query the same S3 datasets directly, eliminating the need for data copying, reducing the risk of data staleness, and ensuring consistency and governance across all environments. This approach not only streamlines operations, but also drives significant cost efficiencies. Security and compliance are paramount in this federated environment. By integrating Redshift Spectrum with AWS Lake Formation, you achieve fine-grained access control across clusters. Each cluster can enforce its own IAM roles and lake formation policies, ensuring secure, compliant, and auditable access to shared data. Metadata management is handled through the AWS Glue Data Catalog, which acts as the metadata backbone for all Spectrum operations. In multi-cluster scenarios, it's essential to coordinate schema evolution and versioning to prevent conflicts and maintain data integrity as clusters operate concurrently. Performance hinges on intelligent partitioning. When multiple clusters access the same S3 datasets, aligning partition keys with workload access patterns enables effective partition pruning, reducing S3 scan costs. This is a critical optimization for large-scale, concurrent workloads. Because Spectrum queries data directly in S3, result sets are not cached across clusters. While this ensures real-time data access, it also means you must optimize queries to avoid redundant S3 reads. Spectrum's architecture allows each cluster to independently execute queries on shared datasets, supporting workload isolation and horizontal scaling. These architectural patterns enable organizations to achieve scalable, secure, and cost-effective analytics across a unified data lake, empowering teams to innovate without compromise. Fine-grained access control is a cornerstone of secure, multi-tenant analytics with Redshift Spectrum, and AWS Lake Formation integration makes this possible at scale. With Lake Formation, you can centrally define column, row, and table-level permissions, ensuring that each user or group can only access the data they're authorized to see, even down to individual rows or cells. Role-based access control is further enhanced through scoped IAM roles. When you create an external schema in Spectrum, you can specify which IAM role the query should assume, or even map specific roles to query groups or user types. This ensures that each query operates with the minimum privileges required, upholding the principle of least privilege and reducing the risk of unauthorized access. S3 bucket policies and KMS encryption work hand in hand to secure your data lake. It's best practice to restrict S3 access only to the specific execution roles used by Redshift Spectrum, and to ensure that KMS key policies allow decryption only for those roles at query time. This synergy keeps your data protected both at rest and in transit without exposing broader access than necessary. Although Spectrum doesn't natively support data masking, you can enforce masking into tokenization by exposing only external views that apply masking logic using SQL functions. This allows you to present obfuscated data to users as needed, further strengthening your security posture. For cross-account and multi-region governance, lake formation resource links and shared glue catalogs enable secure access patterns, while resource-based policies and service control policies ensure only trusted principals can access sensitive data. Combined with lake formation's tag-based access control, you can classify and enforce policy by data sensitivity, ensuring robust compliance across your data lake. Finally, schema evolution and metadata lineage controls are crucial in large-scale environments. By restricting Glue catalog modification rights and versioning Glue tables, you can track changes and maintain a clear history for impact analysis and compliance. To achieve optimal performance with Redshift Spectrum, it's essential to proactively analyze and tune your query workloads using a combination of system views, partitioning strategies, and monitoring tools. Redshift provides several Spectrum-specific system tables for deep visibility. Use SVL S3 Query Summary to analyze I/O and duration per file set, SVL S3 Partition for partition pruning statistics, and STL External Query for tracking query sources and metadata. These tables help you pinpoint bottlenecks and optimize workload distribution. Leverage the explain command and system tables like SVL S3 Query and SVL S3 Partition to examine your query plans. These tools help you identify when large volumes of S3 data are being scanned, which often signals missing partition filters or costly data type coercions. Effective partition pruning is one of the most powerful ways to reduce S3 scan costs. Design your external tables with meaningful partitions, such as by date, region, or event type, and ensure your query predicates match these keys. When partition pruning is missed, Spectrum is forced to scan all files, leading to higher costs and slower performance. For a broader view of S3 read patterns, enable S3 access logging and combine it with CloudWatch metrics like getObject and bytes downloaded. This helps you correlate query workloads with S3 activity, identify hotspots, and detect anomalies in data access patterns. Always define your external table schemas explicitly, rather than relying on Glue's automatic schema inference. This reduces runtime parsing overhead and increases query predictability, minimizing surprises during execution. Finally, monitor Spectrum errors and retries by regularly checking STL error and SVL S3 error for issues like malformed files, schema mismatches, or permission denials. These silent failures can degrade overall performance if left unchecked. These advanced monitoring and tuning techniques, you can detect Spectrum-specific bottlenecks early, optimize scan efficiency, and ensure your Redshift analytics workloads are both cost-effective and high-performing. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.